Missing maybe one or two people. 1, 2, 3, 4, 5, 6. We usually have 7 or 8 in here. I think 7. So maybe just Jason missing. All right. All right. And we're missing our distance learning student. One of them. The other one watches the videos later. Excuse me. So we are going to go to the right class, first of all, here. Engineering. So today, chapter 3, assignments are due, all the stuff from chapter 3. Before we get started, does anybody have any final questions from chapter 3? I answered a few questions from different students over the week, but any particular questions about the functions, built-in MATLAB functions? All right, well, if we're ready to move on, then we're ready to move on. Let's get on to chapter 4, manipulating MATLAB matrices. And this really is kind of the meat and potatoes of MATLAB. If you remember from the very first class, I think that I mentioned that MATLAB stands for Matrix Laboratory. And most computers and most computer programs, when you're doing calculations of large sets of numbers, like a matrix full of numbers or an array full of numbers, most programs are designed to do the calculations element by element by element. So if you have a matrix that has 1,000,000 elements in it, has to do 1,000,000 calculations. MATLAB was designed specifically to do operations that allow it to do all of that entire calculation at once using what we call parallel computing, right? And you may have heard of the word parallel computing. Maybe you've heard parallel processors, parallel processing. The idea is that instead of making your processor in your computer, the processor, the CPU, instead of making it just do one task at a time, you kind of break it into little pieces. You break the processor into pieces and have it do several small tasks at one time instead of one big task. And it turns out that that's much more efficient. And so now computers now are even designed with multiple processors built into their CPU. Your average computer these days probably has 2 processors, I would guess. I guess that's the most common one out there. I've got 2 computers here in the physics area, engineering area, that have 6 processors. I think most of mine have 4. I don't know what this one has. Let's check to see what this one has. About this Mac. This one has, I think the i3 is a quad processor. So I think this one has 4. And then you can get really big ones. And the whole purpose of that is, instead of having one big computer in your computer, you have several smaller ones. And so programs like MATLAB will know that. They'll look at the computer, the CPU, and they'll say, "Oh, that's great." And it'll start assigning tasks in a parallel manner. So say this processor is going to do this one, while this one's doing this one, while this one's doing this one. And it's like running a company where you have a bunch of different people that can do things all at once, and then all come back with the answers all at once, right? And that becomes much more efficient, much faster, and much cheaper, actually. It's a much cheaper way of doing things as well. Cheaper in terms of energy, in terms of money, in terms of time, in terms of whatever, all kinds of things. So that's the reason, the real reason that MATLAB was created, is to give computers a better ability to do parallel processing, to compute many things at once instead of one thing at a time, one after the other. So in chapter 4, we're going to talk about matrices, one of these ways to do all these things at once. The mathematics of matrices, often called matrix algebra or linear algebra or or matrix mathematics, matrix calculus, whatever, is actually not that old of a mathematical thing. It's not been around that long, 100 years maybe ish. People have been using matrices to do things with. Probably a little, I'd say less than that actually. The first textbook written on the subject was written while I was in high school. And I actually took a class on this from the guy that wrote that very first textbook on this subject. So this is not really that old. This, I mean, unless you consider me really old, I guess. But it's not like algebra or calculus that has, you know, thousands or hundreds or thousands of years of use behind it. This is fairly new stuff. And one of the reasons it became so popular is because of the rise of computing, the rise of the personal computer, the computer that you can have at work, which happened to, you know, in the 70s with with Apple and then other companies as well. So let's start. We're starting on page, whatever page this is, 119, defining matrices, which we've done before. We've defined many matrices before, and they just give a bunch of different ways to do it here. I'm not going to go over them again because you've seen them before. One that you may not have seen before is this way of creating a matrix. We're going to create a matrix with 3 rows and a single column. So you could call it a vector if you want. Sometimes when it's only got 1 row or 1 column, they call it a vector. But they do this on this, it's like in the little second part there on page 190. Well, sorry, 120, not 190. A equals, and they put in their first square bracket, and they're going to put in a 1, but they're going to hit enter first and then put in a 1, and then hit enter again and then put in a 2, and then hit enter again, put in a 3. And then, can you see that? And then they put in their square bracket at the end here. And they actually go up in here and they hit a tab before that. I can't do it anymore at this point. But then they hit enter and it does that. Some people like to do that just because it makes more sense to them to build a column matrix using a column. You know, if you wanted to do it again, you could do it like this: A equals square bracket. You could put the 1 here, for example, and then return and then tab, well, space over, I guess. And then you could do the 2 here, return, space over, the 3 here, and then you could close it with a square bracket or something. That gives you the same result. I'm not a big fan of that because you can also just do A equals, put in your brackets, and do just the 1, 2, 3 thing, right? It's just faster to me, but some people like to do it that way. It's up to you, really.
Hey, Jared.
Yes.
Could you share your screen with me?
Oh, yes. All right. Let's see. Zoom. Share screen. MATLAB. Let's just do. There we go. Can you see it now?
Yeah.
All right, here we go. So, so different ways to do that. Some of you have actually already discovered that you can actually insert one matrix into another matrix if you want. And they do this down here on right in the middle of page 120. So they start off with the matrix B. Why am I? B, there we go, B equals. And what is B? 1.5 and 3.1. So 0.5, 3.1. And then they define the matrix S to be equal to, they put in the number 3.0, and then they do comma B, just like that. And so it just essentially adds B onto the end of that matrix S, where 3.0 is the first point, the first element, and then the 2 elements in B go right after that. And you could put B in first and then comma S. The one thing that you can't do is this. You can't say S is going to equal, let's say S equals 3.0 and then do a semicolon, like a new row, because semicolon means new row, and then put in B. Why can't I do that? Yeah, because what this is going to result in, if we draw it out here really quick, and you see if I can draw it out for you, because MATLAB certainly won't do it. But what this would result in is it would result in a matrix where in the first row we have 3.0, and in the second row we have B, which is 1.5 and 3.1. Well, we haven't told it what this thing is yet. And MATLAB does not just fill in spaces randomly in most cases. So it's not going to know what to put there, so it won't do it. So if I hit enter down here, it says the dimensions of array being concatenated are not consistent. What does concatenate mean? Concatenate means you add something on to the end of something else. So that's concatenation. So, so if you want to do something like that, you will definitely need to have two elements in your first row, 4.5 maybe, so that you have an equal number of elements in both rows, and it knows how to do that. In the first one, we concatenated S by just adding B onto the end of it. In the second one, we concatenated S by adding a next row to it, which was equal to B. It still works that way. You can also go into a matrix and change it. So let's say that I want to change the second element of S. Oops. I do S parentheses 2, and then I just set it equal to something else. Set it equal to -1, which is what they're doing here. And you can see that the second element in S has now been changed to -1. And this should tell you how MATLAB counts the elements in the matrix. How do you think it counts the elements? Does it count across the row first? It counts down the columns first, right? So this is the first element. This is the second element. This would be the third element. This would be the fourth element. So if I wanted to do S, I believe this should work. S4 equals -1. Then it puts this fourth one over here as -1 as well. But there's another way to do it. When you have a square or a rectangular matrix that has two dimensions, it has rows and columns, you can also say S, and you can put in two numbers. The first number would be which row you want to change. The second one would be the column you want to change. So if I want to change the element that's in row 1, that's this row, column 2, which is this column, that would be this element right here. And I could change that to equal -1. And it would change that one. So multi-dimensional matrices, you can change two different ways. You can change it by the element number, which is counted from the top left element going down the rows to the right. Or you can do it by row, comma, column, and call it out that way. Most people use this version because most of the time when you're dealing with a matrix in MATLAB, it's a big matrix and you don't want to mess with which one is this, counting all the way down all the columns. That's just a really messy job. So usually people will call it out using the row column call out option. Okay, so what else here? We've already done this, so this shouldn't be terribly new to you, but you can use the colon operator. So the colon operator will create an array of numbers, and you can do it inside of square brackets or outside of square brackets. So 1:8 will give you an array of numbers that starts at 1 and goes to 8 in integers. Here's something that I can't remember if I've shown you before, but this is the suppression semicolon, right? If you put a semicolon at the end of a line of code, it suppresses the output, so it won't print anything to the screen. And that's useful, especially if you're making a huge array and you don't want it to show up. So like, let's say if I make the array infinite mess equals 1, oops, equals 1 to 1 million, right? 1, 2, 3, 4, 5, 6. And I print it out to the screen. Not only does it make a huge array of numbers and prints it out to my screen, but it takes time to print that all out to the screen. So it's kind of messy. But if I do the same thing and put a semicolon there, it's done. And over here, it stores that array. That array is stored in here, but it didn't print it to the screen. So it takes less time and it puts less mess on in the command window. So that semicolon operator is kind of useful. And also so the other way that you can do that is you can say, well, h equals 1 colon 8, but instead of leaving it open like this, you can put square brackets around it, and it does the same thing. It doesn't change anything about what it does. So both of those commands are totally valid. You can also, this one that you've all seen before as well, where you can choose the step size. I can go from 1 to 8, but I can do it in steps of 0.2 or something, right? Like that. Usually when we're using the colon operators like this, we like to make sure that we put a 0 in there just because it makes it a little more clear what's going on. And some people really like to put spaces in between these just because it looks a little bit messy with, it all put together. I usually don't, but some people do. And that gives you the following matrix in steps of 0.2. This is going to become very useful when we want to calculate something that's going on over time, right? So if something's happening, for example, if you have, I think in your homework you had an equation that looked like P equals P naught exponent to the RT, right? That was the rate equation, we call that. So it looks like this. This essentially is, this is a standard growth equation. So things like fungus grows like this, e to the RT, where T is a time. It can be time in years or time in seconds or time in whatever. And this R here is essentially the thing that tells you how fast this thing is growing. And this thing always results in this growth rate that starts off kind of slow and then kind of explodes upward. And the P naught tells you where it starts. That's the starting point here, essentially. The R tells you how steep this curve is. And the time is along this axis in these little steps in time. Well, if you want to do this for 10 years, but you want to do it every day of 10 years, right? Well, then you want to create an array of days that's 10 years long. Well, there's 365 days in a year, and 10 years would be 3,650 days. So plus, some leap years. But you could easily make a time index that says T equals, if I can go back to this maybe, go back to my screen here, T equals, and I could start from 0, from day 0, and I could go in steps of 1, and I could go all the way to 3,650 days. And if I want to add on a couple of leap years, I can do 3,652 days. And that would give me an array of those numbers in that time in days. And if I wanted to do it in half days, then I could actually do it with another thing here and do a 0.05 or a 0.5 rather, a 0.5. Put a 0.5 in here and another colon, and that would do it in half days, right? Or whatever. We create an array of numbers that then I could use that array of numbers to calculate this value here. If my R is, say my R is 0.1 or something, then I plug in T into this thing just as this array, and I can get a whole array of numbers of how much it has grown, how big it is on those half days. Okay, so the colon operator Now, something else about the colon operator that is really quite vital. Let's create an array of this. We're about three quarters of the way down 121. We're creating an array m equals. We're going to create a rectangular array, and they're going to do it like this, where they. So I'll do it that way too. 2, 3, 4, 5, 6. And then bottom one is 3, 4, 5, 6, 7. Okay, so we've made this nice little array here. That's what it looks like. Now I can actually extract things from this array because the colon operator also has another meaning. It's actually the same meaning, but it's not obvious that it's the same meaning, but it can be used kind of backwards. Let's say that I want to say that x equals, I'm going to take something out of the M array. And normally when I want to take something out of the M array, I just put in a number here that tells me, so if I want to take out the first element, for example, I just put 1 in here, and that means x equals the first element, which is 1. Or I could do the third element, x equals m3, which is 3, because 1, 2, 3, that's the third element. That's that one. Or I could even use two numbers. I could do 3, 4. So my x is now going to equal the third row, fourth column. It should equal 6. And it does, right? And that's how we usually do it. But I can also extract an entire row or an entire column. And this is how I do it. Instead of putting in 3, 4, I put in colon operator, comma, 1. What that tells me is it says, give me everything in column 1. The colon means everything. Excuse me. The colon means everything, step by step through the rows. So it's every row, but only the first column. That's what the colon operator means. I've never tried this before, but if we do m colon, let's see what it gives us. Yeah, it just gives us the whole thing, right? It gives us every row and every column. I've never tried that, but it knows what to do. It's not surprising. But we could also do the first row and every column. If we do the first row and every column with the colon operator, then it gives us the first row. And really, that's what it means. That's what the colon operator means. If I say that A equals 1 colon 8, what I'm really saying is that A equals 1, every number between it until 8 in integer steps, right? So they really is the same meaning, and it is the same kind of operator in MATLAB, but it's used in different ways when it's used inside of the call, when you're calling something out of a matrix. So the colon operator. Here's another one we can do. We can do, this is about halfway down the page on 122. So we can call multiple things out of M, multiple rows, multiple columns. I do this all the time. So they're doing M2 colon 3 comma colon. So what should this do? Remember that the first thing before the comma, and this should be parentheses, not square brackets, sorry. Remember when you're calling something from a matrix, you use the name of the matrix and then parentheses. Inside the parentheses, the first thing you put in before the comma is going to be the row that you're calling. The second thing is going to be the column. So what are we calling here? We're calling rows 2 to 3, everything from row 2 to 3, and what? With the columns. All of the columns, right? So this should give us all of row 2 and 3, essentially, right? And that's what it does. You can also do it, you can also call, so they're doing 2 to 3 and then 4 to 5. So we're just going to call rows 2 and 3 and columns 4 and 5. Well, rows 2 and 3 would be these two rows, the bottom two rows. Columns 4 and 5 would only be these last two columns, right? So we should just get these numbers here. And lo and behold, we do. 5, 6, 6, 7. Now here's an interesting one. If we call the matrix M and just put a semicolon in there, it actually transforms the whole thing into just one long column of numbers, right? 1, 2, 3, 4. Oh, sorry, 1, 2, 3, 2, 3, 4, 4, 3, and it does it column by column. So it does the first column, then it reads out the second column, then the third column, then the fourth column, then the fifth column, and puts them all in one column, one after the other, like that. All right. If you want to do a row like that, you just do the same thing, and then you put a single quote after it, puts it into a row. Okay, so yeah, column operator, the colon operator. In this next example, they do a thing with temperatures, and this is actually fairly similar to something you'll do in the homework, where I'll give you a data file of temperatures, or you are going to make one. I can't remember if you make it or if I give it to you. And then you're going to calculate from those temperatures, or you're going to extract from those temperatures different things like you're going to extract the first row and calculate the mean, or extract the third column and calculate the median or something. And so they just have you doing different things like that by extracting different things to calculate. And this becomes quite important because, as you well know, when you're working with matrices or charts full of numbers, oftentimes you have something looking like this, where you have like an Excel file, for example. If you have an Excel file and you have your first column here, and then you have your second column and your third column and your fourth column, and so on and so forth. And we all know how this works. The first column maybe is the date, right? Maybe that's the date. And maybe this is the time. And maybe this is temperature. And maybe this is rainfall. And maybe this is humidity, right? Or whatever. There's all these different numbers. And if you want to calculate something using these numbers, you need to know how to extract something from the third column and from the fourth row and an entire row. If you want to calculate all of the temperatures from all the days, then you extract this entire column. But maybe you want to extract both of them so that you can keep the dates with the temperatures and know what they are. But but if you just want to calculate something from a single day, then you can use just this row. Or if you want to calculate from a series of rows, like everything from day 1/9, January 9th to January 18th, then you extract all of these rows and all the columns in those rows, right? So now you can do something like that. Okay, so now we're going to do something that most students find quite confusing. And it's okay to find it confusing because most people do. I'm going to try to explain it the best I can to try to illuminate your minds to the idea. But we're going to do two-dimensional mathematics, two-dimensional calculations now. If you've taken Calculus 3, this might not be too big of a stretch. And maybe if I explain it right, it won't be too big. If I explain it well, it won't be a big stretch. But But don't be afraid to ask questions. Don't be afraid to try to take some time to figure these things out, because it's certainly not intuitive. All right. So 4.2 on page 126. So we're going to go ahead and assign some variables. X equals 3. There's our first variable. Y equals 5. Actually, what I'm going to do first is I'm going to clear everything out. I'm going to clear everything, clear all my variables. Then I'm going to do X equals 3. I'm going to do Y equals 5. I'm going to do A equals X plus Y. Nope, that's not what I was supposed to do. I was supposed to do X times Y. There we go. So A equals 15 in the end, right? Now, that's simple. We've done that before. But what if I change it to this? X equals 1 to 5. So now X is an array of numbers, right? Just to remember what that looks like. That's what X is. And now we're going to do A equals X times Y, right? So what it's done is it's taken Y and multiplied every number in X times Y. So 1 times 5, 2 times 5, 3 times 5, 4 times 5, 5 times 5. Great. What if I say Y equals 1 to 3, right? And then I do A equals X times Y. Doesn't like that. Matrix dimensions must agree, and you've probably seen this at some point in your homework. I know that a few of you have, and I'm pretty sure probably all of you have. It's not sure what to do with this because you have one matrix that's 1 by 5, one that's 1 by 3, so it's not sure what it's supposed to be doing. So what if I create a new Y using my linspace, excuse me, using the linspace command or linspace function? Remember that the linspace function, if you do linspace 1 comma 5 comma 3, 1 comma 3 comma 5 actually, did that backwards. It will give me 5 numbers between 1 and 3, starting at 1 and going to 3, and they will be evenly spaced. 5 numbers between 1 and 3. So I hit that, that's what I get. Turns out if you go by steps of a half, that's what you get. So now I can actually do some multiplication. I can do A equals X dot Y, but I need to do X times Y rather. I need to do a dot times so that it knows what kind of multiplication I'm doing. At this dot times tells me to take the first element in the first matrix and multiply it by the first element in the second matrix to get the first element in the resulting matrix. So A is going to be, A is now going to be X, which is 1, times Y, which is 1, so it'll be 1 to start off with. And then it'll be 2, which is X, times Y, which is 1.5, which is 3. And then it'll be 3 times 2, which is 6, and so on. So it takes it element by element, it multiplies them element by element. First element's multiplied, second element's multiplied, and so on. So this is all kind of review. We've been here before. The next step is not review, okay? The next step is not quite review. So we're going to go back to our original Y equals 1, 2, 3, essentially. Oops, square brackets. We're going back to our original Y, 1 to 3, and we're going to create some new vectors, some new matrices that will allow us to multiply X times Y without making a new y necessarily. We're going to make a new y, but it's going to just be this one over and over again. This is what it's going to look like. The new x, we're going to just call new x. There you call it new underscore x. Just call it nukes. New x is going to equal the x vector printed over and over again in rows. So it equals, shoot, no. There we go. New x is going to equal this array of numbers that goes 1, 2, 3, 4, 5. Then on the next row, it's going to go 1, 2, 3, 4, 5. And on the next row, it's going to go 1, 2, 3, 4, 5. So it's the x vector in 3 different rows. Just like that. Then I'm going to make new y. New y, new underscore y. There we go. Can't type today at all. I'm usually bad, but not this bad. So then I'm going to make now the y vector. I'm going to make it the same size as the new x. But instead of putting the y vector in the rows, I'm going to put it in the columns. You notice that I only put three rows in this new x. And that's because I have 3 rows in y for 1 column. So I want to do 1, 1, 1, 1, 1, 1, 1, space, 2, 2, 2, 2, 2, 3, 3, 3, 3, 3, right? So new x has x in every row. New y has y in every column.
Hey, Jared.
Yes.
How do I make the numbers line up like that so they're in rows and columns?
Like when I typed it in here,
Yeah.
I just, at the end of the first row, I hit enter and then I spaced over and I put in the 2s and then I hit enter and spaced over and put in the 3s and then put in the square bracket.
Okay.
That's all I did. So now I can actually multiply these together. Let's try to do it. New underscore x times, and I'm actually going to use, I think I'm going to use times. New y, see what happens. So let's just multiply them together and see what happens. So incorrect dimensions for matrix multiplication. So this is not the same thing as the last error I got. Previously, I tried to multiply x and y and said dimensions do not agree. This is a different error. This says incorrect dimensions for matrix multiplication. It turns out that I can multiply these together. New x times new y, but I have to put new y as its, I have to make its, what do they call it again? The complement, whatever it's called. But I have to put this thing on the end of it, and then it'll actually do the multiplication. But notice that the answer is not the same size as the 2 original matrices. This is not something you need to understand why it happens, but it is necessary for you to understand that MATLAB knows how to do matrix algebra, even though we don't. So it's following rules that it understands about how to do matrix multiplication. It can do matrix, all kinds of things. It can do matrix division, matrix calculus. I mean, it can do all kinds of matrix stuff. And so that's why you're getting these errors where the matrix dimensions don't agree or error using this thing. We're not going to study that in this class. We're not going to make you learn how to do matrix calculations. But I want you to know that that's why you're getting the errors, because MATLAB is thinking that you're trying to do matrix mathematics, but you're not. What we're trying to do is we're trying to multiply them element by element. We're trying to extract these numbers out by doing kind of normal types of multiplication. So let's do that multiplication again and use the dot times that we're used to. oops, we have to take off the prime there. There we go. And this gives us what we expect. The first element times the first element, x, first element times y, new y, first element, 1, 1, gives us 1, right? And then we get 2 times 1, which is 2. And 3 times 1, which is 3, and so on and so forth. Well, that's great. That does exactly what we thought it would do. It multiplies things element by element. But notice something else. If we go way back here to where we multiplied these two things together before we made them into matrix, we got 1, 3, 6, 10, 15. 1, 3, 6, 10, 15 right there, right? Let's see. Did I do that right? Oh, we haven't done it yet. Never mind. I was getting ahead of myself. So we'll save the rest of that comment that I was about to make for, I think, the next section or very close to the next section. Okay, so the next example that they do in the book, example 4.2, they're using, let's see, are they using mesh? They talk about using mesh grid at the bottom of 128, but I'm trying to see if they use it in the next two examples. It doesn't look like, oh, they do. They do use it in example 4.3. I don't see them using it in example. Oh yeah, they do use it here as well. So we need to actually go through these examples. Okay. So in order to do the math that we were trying to do earlier, and to kind of shortcut this method to allow, since MATLAB is working in this kind of matrix environment that we're not used to, and we're trying to work in the regular math environment that we've always been used to in the classes we've been taught, there needs to be something that kind of bridges that gap, that allows matrix to have the numbers it needs to do the calculations the way it does calculations, but allows us to plug things in the way that we're used to using regular math. Because we won't always be using matrix algebra, and sometimes people that are using MATLAB are not really that familiar with matrix mathematics. So the function that bridges the gap is a function called the mesh grid function. And the reason it's called mesh grid is because what it's going to do is it's going to do kind of what I just did with the new X and the new Y. It's going to take an array of numbers that is a 1 by something row array, and another array of numbers that's a row of numbers. And it's going to create a matrix out of them, like I did, where you have this matrix that has everything in the same row repeated over and over again, and then another one where the same column is repeated over again. And then you're going to be able to use MeshGrid to do some mathematics with those matrices that makes sense to MATLAB so that it can use it. And then we'll spit on an answer that makes sense to us. So it is really this kind of thing that is bridging this gap. So let's go ahead and do this. Let's do this example so we can see how this works. Example 4.2, distance to the horizon. So we have this equation that they give us, r squared plus d squared equals r plus h quantity squared, right? And if we solve this for d, we get the equation just below it. And that d is the distance to the horizon on a particular planet with a radius r, where height is the height you are above the planet's surface. So whenever I'm doing problems like this, and I've actually had a few people ask me questions like, how do I, get started on a problem like this? I always write things out first. I do it just like I do any math problem or any science problem. I start to write things. I start to draw pictures. And in this example, they do draw a picture. They draw a picture of a planet, and they show, the height of the mountain or whatever, h. And I would literally draw these things out, and I would recommend that you do it. And then you have the distance to the horizon is this distance. Oh, I just lost my mouse for some reason. This mouse has been giving me all kinds of trouble. It's brand new. Maybe I need to get a new one. Yeah, that's why I plugged in this one, so I could use it if I needed to. So the distance to the horizon is this. That's not a very good distance to the horizon. It's this distance here, though, out to the horizon, whatever that distance is. And the radius, of course, is the radius of the planet here. That's not a bad picture. It's much better in the book. And one of the things that is good when you're doing computer programming is to define your inputs and outputs. And we have this equation, and I'm going to write the equation first that they wrote, that they solved for. D equals square root of h squared plus 2rh. Yep. Okay, so the inputs, we're trying to calculate the distance. That's the thing we want to know. So we're inputting the radius of planet. In this case, they're doing radius of a moon, actually. Right? So that's R. And then the height is the height of the mountain. Sorry, my handwriting is even worse on a computer than it is in real life. Height of the mountain. And then oh, they actually have two radiuses here. Which one is the radius of the moon? Which one's the radius of the Earth? From this last expression, the distance to the horizon is the Earth. I don't understand where the radius of the moon comes into play. Is anybody seeing something I'm not seeing? I only see one R in there. Height. Oh, it wants us to do two of them. I see that. I see that where they're talking about that now. Okay. Yeah, that makes sense. Okay. So I'm going to put here the radius of interest. I don't like the way they've written it. I like this way. In other words, there's more than one radius. Interest. This is the height of the mountain, right? So we only have two inputs. And then the output is going to be just one output is D, right? The distance to the horizon. And of course, we have our equation already for this. When you're doing something with a formula or an equation or a function, a mathematical function of some kind, you need to define your inputs before you create your function, before you actually call for your output, right? So we need to define what R is going to be and define what H is going to be. Now, what height do they want to do? They want to do height of the mountains. So this is two of them. I'm going to put in the two, radius of Earth, radius of Moon. But they actually want a specific range from 0 to 8,000 meters. And I don't know if they say what, no, they don't say the step size. We can do it 1 meter at a time or 5 meters at a time, whatever we want. But both of these are now going to be arrays, right? We're going to put two radii in, and we're going to put in, maybe 8,000 different heights, or maybe half that many. It depends on how many steps we take in between 0 and 8,000. But we're going to come out with just one number. So we're putting a bunch of numbers and a bunch of numbers. We're coming out with just one number, right? So the first bit of code is going to look like this. Radius equals the radius of the Earth, which is a number they give us, radius of the Moon or Earth, whatever one you want to do. I did Earth first, so it'll be 6378 for the first one. And that's kilometers. So 6378 kilometers, you have to add 3 zeros on it to make it equal to meters right there. And let's see, are they saying that the radius is in kilometers? They're doing it all in kilometers. We can switch to meters. I just switched it to meters, but they're doing it all in kilometers. So that means we're going from 0 to 8 kilometers here. So if we do it their way, we just do it with kilometers. It's totally fine. So 6378, right? And then we do a space or a comma, and we do our radius of the moon, which is 1737. So there's our first one. And so far I haven't even typed anything in. This is all stuff that I would write down on paper as I'm doing a more difficult problem. And then I'll do my height. My height is going to equal 1 to 8,000 or 8 kilometers because I'm doing this in kilometers, or 0 to 8 kilometers. Or I might want to do it as 0 and do it in tenths of a kilometer, because this would only give me 8 points every 1,000 meters. But if I do it in tenths, then it gives me every 100 meters. So 0.1 to 8 kilometers or something like that. And you can choose that. What do they do? I don't even know. They're doing it in steps of 1,000, and they're actually typing in everything in terms of 1,000. And then they divide later. That's kind of dumb. Why would they divide later? But anyway. So then the next thing I'm going to say is I might write down here, after I've started this problem, I might write down, this gives me, this gives matrix dimensions that don't agree. Because I know that this matrix is different size than this one. This one is a 1 by 2, and this one is like a 1 by whatever it is, 90 maybe. This is a 1 by 9 matrix. So these things are not the same size matrices. So when I try to do math with them, it's not going to work. So I might write that down. This gives dimensions that don't agree. I'm going to have to use MeshGrid, because I know that MeshGrid fixes that for me. It fixes matrix problems when I'm trying to just do regular old math. So that, and that's something you might even write in your code in the comment lines, just so that you know why you're doing something. But definitely when you're doing more complex code, as we're going to start getting into, you want to start writing it out on paper. This is what we call pseudocode, and we're going to give you some more examples of how to do this in a couple chapters when we get to really complex stuff. But it's always a good idea to write things out and kind of get an idea for the problem as you're getting into more complex problems. Okay, so now that we get into the code, they've got a bunch of commentary in here that I won't put in, but I will clear all my variables out. First, I got to get to my screen here. And I'm going to go ahead, and they're actually using bank formatting. I don't know why. Let's do that, I guess. So they're using the bank formatting, and then they're going to define their height. So they're actually using height instead of h, and they're going to say they're going to go from 0 to 8,000 in steps of 1,000. So we could actually go to 8,000. There we go. So this actually gives us this array of numbers, 0 to 8,000 in steps of 1,000. But if you look further down to the very next line of code, actually, they redefine height. They say height equals height divided by 1,000, which gives us this one, 0 to 8. So we could have just started with height equals 0 to 8, and it would give us the same thing, right? And that's what I did when I was writing it down. Either way works. So they've just written some code that just is a little bit repetitive. And the reason that they do that is because they're doing everything in kilometers. They're keeping all their units the same. And that's more a physics thing than a code thing. Then they're going to define their radius one. So radius, their radius vector is going to look like 1787 or whatever, 1737, comma 6378. So there you go. So there's the radius. And obviously these two vectors are not the same size. They're, one of them has 7 columns in it. The other one has, no, so one of them has 9 columns in it. The other one has 2 columns in it. Two things in it. So we're going to have to do something else. We're going to have to create a situation where we can multiply these together somehow and it makes sense. And this is where we're going to use MeshGrid. So this is how you use it. We're gonna create 2 new variables, and we're gonna call them capital radius and capital height. So one of these things is gonna have the radius information in it, and one of them is gonna have the height information in it. And we're gonna say that's equal to, and we're gonna call the MeshGrid command, MeshGrid. And then inside of MeshGrid command in parentheses, we're going to put the 2 things in that we want to make into new matrices, radius, comma, height, with the little lowercase letters. G, H, T. There we go. And let's see what that makes for us. So what it did is it actually recognized that the radius vector has only 2 things in it, and that the height vector has 9 things in it. So it made 2 by 9 matrices. In the first one, which is called radius, and it's made from the radius vector, it made a row, or it made a column of the radius of the moon and a column of the radius of the earth. 9 elements, all the same in each one. In the height one, it made a column of all the heights from 0 to 8. 0 to 8. Now, can you see why this is useful? Now we can multiply these things together and we can get radius of the moon times 0, radius of the moon times 1, radius of the moon times 3, radius of the moon times 4, radius of the moon times 5, element by element. And then when it goes to do the next column, it'll be radius of the earth times 0, radius of the earth times 1. It's going to do all that multiplication for us. And in the end, you'll see how we get an answer out that makes sense. So we've made this now. We've made these. So big R radius is now this thing. Big R or big H height is this thing. Now let's go do some mathematics with it. So we're going to say that we're going to use the formula that we had before, the distance formula, distance to the horizon. We're going to use the square root function we've seen before. And inside the square root, we're going to put all this stuff. We're going to put height. And remember, we have to use dot times. So we're going to do dot, or dot times dot squared. We're going to do dot squared. Sorry, this is dot squared. So we're squaring the height. And then we're going to add to it 2 times the radius to the height. So we add 2 times. We don't have to use dot times because 2 is not it's not a matrix. 2 times height, then we have to use dot times because we're multiplying matrices together, big R radius, and that's our formula. And look, now we have the distance from this. These are all the distances on the moon to the horizon at different heights. These are all the distances on the earth to the horizon at different heights of the mountains. And that makes sense. In the middle, this height and radius stuff doesn't really make sense sometimes. You're like, why did we do that? But we did that so that we could multiply them together element by element. And MeshGrid is a quick way of creating those matrices. When I did it before, I actually had to do them by hand, right? When I did it with the M matrix or whatever I was using before, no, the X and the Y matrix before. I had to make that new X, new Y, and I had to do it all by hand, but then I could multiply them together. In this one, I can use MeshGrid and it does it automatically. It automatically looks at the size of the matrices and creates the matrices that will work. and then you don't have to worry about it. That's what MeshGrid does. One of the things that confuses people is the name of MeshGrid. Why is it called MeshGrid? So the reason it's called mesh is it takes these two matrices and it looks at their sizes and meshes their sizes into a matrix that includes both of their sizes. That's the mesh part. The grid part is it makes this grid or this matrix that can be multiplied together to do math with those previously non-matching matrices. So that's why it's called MeshGrid. When people think MeshGrid, they are automatically thinking something visual, like, you know, a pan or like a cooling rack, or, you know, the thing on a barbecue, the grid over a barbecue, or the grill over a speaker. And they're trying to figure out why this has a mesh grid into it. I mean, even that could make sense if you're understanding what's going on, but I've had so many instances of just trying to figure out what is MeshGrid, but that's what it does. It's really simple in the end, but it's quite important. They do another example of this for free fall. They have another equation. They have another set of, you know, two sets of variables that they want to mesh grid together, and they use the mesh grid command together again. Different gravitational pulls on different planets in the next example. So does anybody have any questions about what we've talked about so far? Because we haven't really talked about much. It's mostly just about, you know, basic matrix stuff that you knew, and then how we're going to build this new mesh grid set of matrices. Anybody have any questions about this? We will see this mesh grid function used over and over again in calculations in this class. So you won't be, it's not the last time it's going to be seen for sure. All right, so section 4.3, back to some kind of special matrices. We've done this before, the zeros function, right? If you use zeros and you put a number in it, it makes a matrix that is 9 by 9, since I put 9 in there, and it's just filled with zeros. And that can be very useful if you need to fill a matrix up during a program. So if you're creating all those answers that we just created, and then you're going to put them into another matrix, sometimes it's a good idea to have a matrix full of zeros ready to accept those numbers, so you can put those numbers into it. There's also other reasons for making a matrix of zeros, but that's probably the most common, is to just kind of placeholders for numbers that you're going to plug in later. You can also do a matrix of ones. It's just the function ones. So you could do a 9 by 9. Well, that's a 1 by 1. You could do a 9 by 9 matrix of ones as well. And you can do a matrix of either of these of multiple sizes, all kinds of different sizes. So if I wanted to do ones, I wanted to do it 3 by 4, I do 3, 4, 3 rows, 4 columns, and it'll do that too. So this one is interesting. I just put in this. I'm trying to illustrate for you something about MATLAB that I've hinted at before, but I've not really shown you. But you can actually have matrices that are more dimensions than 2. So you can have rows and columns, and then you can have actually layers behind that as well. So you imagine, instead of just having this rectangle with numbers this way and this way, you have a cube with numbers this way, and going into it, right? And so in this particular case, you have all the columns, or sorry, where did this one come out? Here we go. So in this one, this is all the columns and all the rows in layer 2, right here. This is all the columns and all the rows in layer 1. So this is like the front face of that cube has this matrix in it. And then if you take one step back into that cube, there's another matrix, and it's this matrix. And MATLAB can do this pretty much indefinitely. I mean, the only limit is the computer. So that you can make multiple dimensions inside of matrices. And MATLAB doesn't care, because it doesn't know anything about the space that we live in. It doesn't know anything about three-dimensional space. It can make an 8-dimensional matrix. It doesn't care. It just keeps storing things and calls them something else. So let's just to make it really crazy, let's do a 5-layer deep. So they actually call these layers and then drawers, and then actually I'm not sure what they call them anymore. I've heard it different ways, but anyway, they have different names for all these. The first one is rows, the second one is columns, and then the third one is something else like layers, and then maybe drawers, and then files, and then I don't know what it is. But whatever it is, it just keeps doing it. It just keeps creating this matrix. And if you try to open this up, it's very different than the one we've looked at before. It doesn't come up as a chart anymore because it can't. There's no way to do it for this 2-dimensional screen. You can't actually plot it out on a 2-dimensional screen. So it has to plot it out as different values at different points. But anyway, just to illustrate that MATLAB can do that. And it is quite useful, actually. All right, so let's actually talk about why that would be useful. Let's imagine that you wanted to create an array of photographs. Have you ever seen these big pictures, these big murals, and every pixel of the mural is made of a photograph? So if you zoom in on the picture, you actually see pictures of people or pictures of boats, and the whole picture is a picture of a penguin or something, right? That is actually a 3-dimensional array, where each pixel in that array has a value. It's in the first row, third column, or the 38th row, 78th column, or something like that. Each picture is an element of a 2-dimensional array. But each one of those pictures is actually an array itself. Each one of those pictures has its own pixels. So it's its own array. And actually, each one of those pictures is a 4-dimensional array because JPEG images are 4-dimensional arrays. So this is actually very common in computing to have multiple dimensional arrays. If you open up a JPEG file in MATLAB, you can actually see that the first layer is a 2x2 array of numbers, and they're numbers between something and like 37,000 that represents the brightness of the red pixel. And then the next layer is the brightness of the green pixel. And the next layer is the brightness of the blue pixel. You have red, green, blue, RGB, right? And then there's one more pixel that represents something else. I can't remember. I think there's one more pixel that is a black. No, that's not it. It's a RGB. JPEG may actually only be 3. I think it's TIFF that has 4, because TIFF can actually store a GPS signal so that you know where that pixel is from a satellite or something like that. But anyway, you know, they're actually multiple layer arrays anyway. Okay, so enough of that. Let's look at some more different types of matrices. On page, what is that page? 134. Yeah. Starting on page 134 and ending on page 134 is a table of different special matrix functions that you can use. We've already done the ones, the zeros, but they also have the diagonal one. So the diagonal function extracts the diagonal of a 2-dimensional matrix. So if I already have a 2-dimensional matrix, let's make it, let's say M equals the matrix. And then just some random matrix, whatever it is. Close it off. I think that's a good matrix. There we go. So we've got some random matrix, and I want to know the diagonal of that matrix. I can actually just say diagonal M, right? And it takes 1, 2, 6, 56, 1. 1, 2, 6, 56, 1. If you have a matrix that's not square, this matrix is square because it's a 5 by 5 matrix. So the rows and columns are equal. If it's not a square matrix, if we say that n equals, for example, the matrix 1, 2, 3, and then 3, 2, 1, and you do diagonal of n, it will actually start in the upper left-hand corner and go diagonally down and then just stop there because it has no other thing to do, right? So it still gives you the diagonal, but it's not a diagonal that goes corner to corner. It just goes from top left corner until it can't go anymore. So that's what the diagonal command does. You can even do a diagonal of just part of a matrix. So if I do diagonal of M, but I extract just part of M. Oops. So I'm going to take all the rows. Let's see. Yeah, all the rows. And no, I'm going to actually do this. I'm going to do from 1 to 3. Sorry. And then 1 to 3. So what I'm taking is just the upper 3 rows and 3 columns of this matrix, right? Then that just returns 1, 2, 6. 1, 2, 6. It's only taking the diagonal of this upper part of the matrix. Okay, and then you have the flip. You have the flip left, right, and the flip up, down, right? Commands. So flip left, right, LR, and you just name your matrix. I'm going to name N. It just takes the right side, flips it to the left side flips it to the right side, and does that with every column in the matrix. And then flip up, down, does the same thing except in the other dimension. Flips the rows around, right? And of course, if you have a matrix that has multiple rows, it does it throughout. So the first row becomes the last row becomes the first row, the second to last row becomes the second row, the middle row stays the same, so on and so forth. And then there's the magic matrix. I've never really discovered a good use for this function in MATLAB, but MATLAB has a lot of things in it that are not really useful. They're just fun. But the magic matrix, if you do a magic matrix of 3, for example, it creates this magic matrix, right? So what is a magic matrix? Can anybody figure it out? It's not random. It's not random. What's that? Anybody in here play Sudoku? It's similar to a Sudoku kind of thing, right? Every single way you go in this matrix, it always adds up to the same number. So it's 15, 15, 15, 15, 15, everywhere you go. If you do the same thing again, magic 3, right? It gives you that answer again because it's unique. There's no other matrix that will do that, but this one. You can change it. You can flip it upside down, left, right. But you can change it by flipping it around, up and down, left and right. But there's no other combination of numbers except for these numbers in this configuration that will be that will do this. The magic matrix for a magic 5 is different, and it has a different number that it adds up to. But if I do magic 5 again, it's the same matrix because there's only one in the universe that does this. So it's kind of Interesting. Very similar to that Sudoku kind of puzzle thing. It has a very particular pattern to it. Now, I've always thought it might be fun to figure out some way to use this function to play a game of some kind. I don't really know I mean, I've never seen anybody use this for anything useful, but it's something MATLAB can do. So I imagine some MATLAB programmer at some point said, I can program this to do this, and I'm going to do that. And then he did it, and now we have it. There's no real reason for it, just that he could, right? Which is like one of the main reasons that engineers and scientists do anything is because they can. They don't really have a reason for doing things. They just do them because they can. And then they figure out a reason later. All right, so those are different matrix functions, different special types of matrices. Man, that's the end of this chapter. We're done. We're done early today. Oh, there's something else you can do. There's something else you can do with the diagonal function that I'd forgotten about. And they do it on page 136. And that is if you have a linear, let's say A equals just some linear whatever, some vector, right? Like this. You can actually use the diagonal function to make that into a diagonal matrix with those numbers on the diagonal. So you just put A in the diagonal thing, and it puts those numbers 1, 32, 5, 3 on the diagonal of a matrix where everything else is zeros. And that's actually quite useful because there are many times when you're using matrix mathematics that you want a matrix with specific numbers on the diagonal. So that's a specific function that was designed particularly for MATLAB to do that particular function. So that's kind of useful. All right. Can't really think of anything else that we need to learn about manipulating matrices from this chapter. Mesh grid is by far the biggest deal in this chapter. And like I said, we will use it over and over again. So you'll get lots of practice with it. But for now, we're going to let you have time off a little bit, a little early exit from class. Unless you have questions, if anybody has questions. Or if you want to stay here and work on your homework, I'm going to be here until whenever class is supposed to be over. I'll be here for another hour and a little bit. But so it's up to you. You can stay and work on homework, ask questions. You can leave and go home and work on your homework. You can go party somewhere, do whatever you want. Yep. Can I what? Yes, you can put it on the other diagonal. And you use another function to do that we've just used. Can you guess which function it is? Yeah, flip left, right, right? So you just use a combination of those two and it would give you the other diagonal. And you could also do it so that you can also do a flip up down so that the top left one becomes the bottom left one instead of the bottom right one becoming the bottom left one, right? So you can use the flip combined with the diagonal function to do that if you want. Not something that we'll use a lot in this class because that's more of a matrix algebra kind of thing, but very useful if you're using MATLAB to do matrix mathematics, I can tell you that. So it becomes very useful when you get into more advanced math courses. Yeah, and take a soda with you if you want, or grab one if you're going to work on homework right now. Are you looking at this stuff on the whiteboard? I don't remember which number that is, but
It's one of the ones that
yeah, that's one that we were working on earlier. Yeah, actually, if any of you want to come in early to work on homework before class, you're welcome to come in as well, because I'll be here. I've had at least 2 people come in and get help before class. But does anybody have any particular questions for me right now? Okay. If there are no particular questions for me, I'm going to go ahead and end the video so I can upload it. Let's see. Do you have any questions, Logan? Can't hear you.
Sorry about that. What page is the chapter 3 homework on?
Chapter 3 homework starts on page 140. Oh, sorry, chapter 3. Sorry. Chapter 3 starts on 112. Does anybody need copies of the book for the homework this week? Logan, did you get a copy of the book?
Yeah, I finally got mine. It finally came in yesterday. So
Is yours the latest version of the book, which is, well, is yours the 5th edition?
yeah.
Okay, so it should be the same page as I just told you. 112. This one, which number was it? Number 9?
Someone may have this or that. What is this?
Okay, so this is just a name of a variable that I'm defining. So what's going on in this whole thing is this is just to illustrate what the primes function does. If I put in primes 5, it tells me all the prime numbers that are 5 or less. So 1 is a prime number, 2 is a prime number, 3 is a prime number, the next prime number after that is 7. So that's it. 1, 2, 3. That's what the output looks like this. 1, 2, 3 with brackets. That's what MATLAB gives you. So we're going to use this function to define 2 variables. The first one we're going to call primes 1. Primes 1 is going to equal to all the primes that are less than 10,000, right? So that's going to be a boatload of numbers, right? Primes 2 is going to be all the primes less than 20,000, which is going to be a boatload of numbers and a few more, right? And if I take all these numbers that are all the primes that are less than 20,000 and all the primes that are less than 10,000 and find out how many of them are, I can use the length function to do that. So I say L1 is going to equal the length of this number. It's going to be how many, this is going to give me how many are in this thing, right? This is going to tell me how many are in this thing. And if I take the number of things here minus the number of things here, then I get the answer. So I did this 2 different ways. This is the first way that I did it, right here, where I just took the length of the first one, or the second one, and I subtracted the length of the first one. That will give you the answer right there. Or you could define L1 as the length of the first one, L2 is the length of the second one, and define a new thing as the difference between the 2. So these are 2 different solutions kind of mixed together. Sorry about that. That's probably what confused you, right? So you have 2 choices here. You can either do this one, this method, or this method. You definitely want to have something like this. I mean, the shortest way to do this program is you could do this whole problem in 1 line of code, but it would be a messy line of code. Would you like me to write this out in a little cleaner version? Because I can do that.
I understand it, but it's not letting me.
Just take a look.
I tried to say.
You put my mask on, so I'm doing it properly. COVID safe person. So A is prime to that, B is prime to that. L is the length of A, L is the length of B. Length A minus length B, that should be your answer right there. That should be the answer.
So just this one thing.
And that gives you the same thing, it just calls it, non-primes. Now, so you don't need both of those lines, you either need, the last line and you keep L1, L2, or you need this second last line, and you can get rid of L1. This will be the same image.
Okay.
All right. All right, I got to stop my video at some point here. How do I stop my video? Pause, stop recording.